Out sections 1 and 2, I asked you guys to work on problems 1 through 40. Let's start with questions from there. Sound good to you guys? Jose.
Number 19, please.
Sure. So 19 says, find the unit vector in the same direction as the vector indicated below. Write your answers in component form as well as linear combination form. Okay. So my vector u is -2, -7. So my unit vector, to do that, I need to find the magnitude of u. So 4 plus 49 is square root 53. So to get my unit vector, I'll call it v for the sake of argument. I'm going to do 1 over the magnitude of u times u. So when I rationalize my denominators, I get this. So this is my answer for part A. And my answer for part B asks for the linear combination form. So that's the form with the i's and j's in it, which is no big deal. All I'm going to do is write it with the x component goes with the I vector, and the j component goes with the y, or the y component goes with the j vector. So that's my answer for B. Yep. And again, if you wanted to, you could write that as just like a subtraction symbol rather than plus a negative, but like whatever.
Okay.
Does that feel cool?
Yes.
Yeah, no problem, my dude. Who's next? Mr. Shearer.
Could you do 38?
38? Sure. 37 and 38 are just kind of a hassle because there's a lot to do, but that's okay. So you're given the vertices for a triangle and asked to find all the side lengths and angle measures for that triangle. Notice that this is like quite similar to a question we could have asked last chapter using the law of sines and cosines. We're going to use vectors to do this, though. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to just start by sketching a picture. 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Okay, so -2, 1. And then -8, -4. And then 5, 7. So I think our triangle kind of looks like that. Notice it's almost a straight line, right? So I'm going to expect, like 2 itty bitty tiny angles and one big gigantic one when I do this. So what I'm going to do is I'm going to come up with 2 vectors at each of these intersections, or at each of these vertices. So I'm going to need yx and then also yz. And if I do the same thing, say here, I'm going to need xy and xz. And I don't really need the third vertex because once I find the angle measures for the other 2, I get the third one for free. And I'll find the magnitudes for the sides along the way to use the angle between 2 vectors formula. So let's start by writing these vectors in component form. So if I do head minus tail, I'm going to do -2 minus a -8. So that's 6. And then 1 minus a -4. So that's 5. And then I'm going to do 5 minus a negative 8, so 13. And then 7 minus a negative 4, so 11. So xy, I'm going to do head negative 8 minus a negative 2, so that's negative 6. And then, well, I guess anyways, negative 4 minus 1, so that's negative 5. You could have also observed that yx and xy are just opposite direction vectors, so you could have just flipped the signs. That's okay, though. Z, so I have head minus tail, so 5 minus negative 2 is 7. And then 7 minus 1 is 6. Okay, so then I'm going to just use the angle between two vectors formula. So angle y is going to be cosine inverse of yx dot yz divided by the magnitude of yx times the magnitude of yz. So let's see, yx dot yz is 6 times 13, so that's 78 plus 5 times 11, so that's 55. 6 squared plus 5 squared is 36 plus 25, so that's 61. And 13 squared is 169, plus 11 squared is 121. So that's going to be 290, I think. And just FYI, I'm expecting this one to be itty bitty little tiny angle from my picture that I drew. Let's see if that's indeed what we get. Notice here that I am not doing any rounding. I think if you tried to round with intermediate answers, you potentially could end up getting errors because you rounded too much. And look at that little tiny angle there, 0.43 degrees. Yeesh. So that's angle y. Notice along the way we got the length for yx and the length for yz. So now I'm just going to repeat the same process here with this guy. So this is going to give me angle x. So negative 6 times 7 is negative 42. And then negative 5 times 6 is negative 30. This we already did. That was the square root of 61. And then 7 squared is 49 plus 6 squared, which is 36. So that's 85. Oops. Negative 42 minus 30 divided by square root 61 times square root 85. So there I get 179.20. And along the way, worth pointing out that we also got xz right there. And then my angle z then is just whatever is left over, which isn't much, but something. 0.365. Does that feel okay, Luke? Just kind of a lot to do, but you know, none of it was like super duper complicated. The nice observation was noticing that you're going to get all the magnitudes along the way to get the angle measures, so you didn't have to do that as a separate set of calculations, because it's like, oh, there it is right there. I already found it. Sergio?
Not about that. Do you have any idea where the clock is just like going nuts?
Stuff's broken. They're trying to fix it. Apparently there's some kind of electrical issue. I'm not sure the details, but it's because we've entered like a wormhole, and now time is behaving strangely.
Yeah, I don't think it'd be that bad if like school went by this fast. Go home.
Boy, it'd be confusing as heck. It's like, well, we were here for the entire day. It felt like it was 5 minutes. I didn't learn a thing.
What if you learned everything like in that fast? That's crazy.
I mean, that'd be kind of terrifying.
Would it?
I mean, think about how hard it would be to process that.
Oh yeah.
How fast your brain would move. Like, imagine having to sit still for 5 minutes then. Like, that'd be agonizing from a relativity standpoint. Be like, oh my God, I'm so bored.
Time is relative.
Anyways, who's up next? That doesn't have like a silly question. Not that it was a really silly question. I just got into a silly tangent. That's my fault, though. I'm a king of tangents. Maybe not the king, the prince. Duke? Baron. I'll call Baron Tangent. That sounds pretty cool. I don't know. I hate to put myself at the top of the pyramid. I don't want to get eaten. You know? Tie it all the way back to the beginning of class on some of my weird tangents. All right. Last call on questions for this. That's okay. We can always circle back if something comes up later. Today, we're going to be talking about section 8.3 and applications of vectors. So we're going to look at several different applications today. The first one is a situation that we're already quite familiar with because we dealt with this situation in first semester. And it's just one of these navigation kind of problems. So let's take a look at this example. So a boat leaves a port and averages 40 knots for 2 hours on a course of 215 degrees. And then the boat turns to a bearing of 162 degrees and travels 55 knots for 3 hours. What is the distance and bearing of the boat relative to the starting position at the port? So the first thing I'm going to do is kind of observe that basically I have two vectors here. Right? The first vector I'm going to call vector u. I notice that the length of vector u is going to be that 40 knots times 2 to give me 80 nautical miles. And if I draw my bearing of 215 degrees, remember bearing starts from due north and goes clockwise. So 215 is like over here. So this little wedge is like 35, right? 180 plus 35 would give me 215. But what we really want is this direction. So in this case, it's going to be 270 minus 35, or 235. My other vector I'm going to call vector v. I notice the magnitude or length of vector v is going to be 55 times 3, or 165 nautical miles. Again, the bearing is from north and clockwise. Means that little sliver's 18 degrees. So the direction I have then is 270 plus 18, so 288. Using this now, since I have written my vectors as magnitudes and directions, I can easily translate those into component forms by doing the magnitude of u times cosine the direction of u, magnitude of u times sine the direction of u, and similarly for v. And now, since I have them both in component form, I can add those two vectors together quite easily. Notice at this point, this is like the exact same steps as what we were doing in first semester. We've just included a little vector notation and vocabulary. So I get 5.10 for the x component. And negative 222.46 for the y component. Now that I have that vector in component form, I can compute its magnitude and direction quite easily. And I get 222.51. Nautical miles. And if I wanted the direction, then I'm going to go ahead and plot the point 5, negative 2222. So that's going to be down here somewhere. The direction is this angle. So to find that, I'm going to find alpha, and the other end of alpha that's on the x-axis there is 360. So theta is going to equal 360 minus alpha, where alpha is the tan inverse of the absolute value of the y component divided by the x component. So if I go to my calculator, y divided by x, close. So I have 271.31 degrees. Note that that would imply this piece was 89.69, and I don't remember if we wanted a direction or if we wanted a bearing in the directions, but I included both the direction and the bearing in the problem. Luke?
Why would 360 be on the far right and top?
So when we go around our in standard position angle,
Oh, okay. And wait, so for then when you were finding out the bearing of the first vectors, were you doing that in standard or were you doing that not? That makes sense.
So I drew the bearings in red, and then I drew the standard position angle in blue.
And when you drew those bearings, you were doing the 0 at top and 90, 180.
Correct.
Okay.
So it starts at due north and goes clockwise, as opposing to starting on the east and going counterclockwise. Serge.
Probably a stupid question, but what's the difference between a bearing and a direction?
The way they're defined,
Okay, well, how's that?
bearing starts
Did you more?
due north and goes clockwise.
Okay.
Direction starts on the positive x-axis and goes counterclockwise.
Okay. So it's just like alpha. Not alpha, sorry. Theta.
Yeah, thetas are the directions. Yeah, like is the direction of an angle. It's just our standard angle form from first semester. Okay. So overall, this shouldn't have been too bad. Should have looked pretty familiar. It's really the same process we used first semester. We've just updated a little bit of the notation and some of the naming, but it's like still the same. Okay with that idea? Before we talk about our next application, we want to define a new vector operation. So let's say that we have two vectors. We'll call this one vector v, and this one vector u. And we want to find a way to rewrite vector u as the sum of two vectors. One vector should be in the same direction as v, and the other vector should be orthogonal to it. So what we're really saying here is I want to break this vector u up into a vector here plus this vector here, where they're at right angles to one another. Everybody observe that this is the way that the vector sum is written, right? Since I wrote the red and green vectors as head to tail, right? So we're going to give this red vector a special name. This is going to be called the projection of u onto v. So what you're projecting onto is the subscript, and what you're projecting with is like the inside part of the function. So that's read as the projection of of vector u onto vector v. And then I'm going to just call this green vector, I'm just going to call it w to give it a name. So what we can say here is that the projection of u onto v plus w is equal to u. Or, if we wanted to rearrange things, we could say that w is equal to u minus the projection of u onto v. So really what we've done is we've broken that vector u up into two orthogonal vectors. So those two vectors, the projection of u onto v and w, will add up to give us u still. And the additional feature we get is that vector, the projection of v onto u, is in the same direction as vector v. So the obvious question you should be left with is, okay, how do I calculate one of these projections then? So for non-zero vectors, u and v, we say that the projection of u onto v is equal to the dot product of u and v divided by the magnitude of vector v squared times vector v. So that's our definition for the projection of one vector onto another. Now, you might think to yourself, like, Mr. Kulik, why in the world, like, what kind of application does this have? And it turns out this actually has a lot of really important applications, particularly in physics. So if you are, like, trying to push one object up a ramp or in a specific direction, and the force you're applying isn't always in the exact same direction as a ramp, or in that same direction, this becomes a really important calculation, as it'll tell you, like, okay, how much are you really pushing in the direction you want? Like, how much is wasted? And we'll do some examples here in a moment to kind of illustrate that. So a couple of finer points here about this projection formula. If I look at this projection formula, it certainly appears that the length of the vector we're projecting onto matters. In a real context, though, it kind of doesn't always. Notice when I drew this vector v, I just kind of drew it arbitrarily long. And the total length of vector v isn't really affected by the drawing that I've made. You know what I mean? So in some cases, and we'll look at some examples of this, so in some cases, that length of vector v doesn't really matter. In those cases, we're just going to assume the length of vector v is 1. That essentially v is going to act as a unit vector. All we really care about is the direction of v. The second piece is, if I look at this projection formula, the dot product of u and v just gives me a real number, right? The magnitude of a vector just gives me a real number. So really, what I'm doing here is just scalar multiplication on v. Everybody's okay with that? That this projection is just a scaling of v. And it's kind of proportionally then to u and v is the scale that we're doing. So again, the two takeaways here is that if the length of v apparently doesn't matter, we're just going to choose the length of v to be 1. We're going to treat v like a unit vector. And then just to remember that this projection calculation is really just scalar multiplication. Let's do a numeric example here to just kind of get used to the calculation. So here we're asked to find the projection of u onto v, and then express the vector u as the sum of two orthogonal vectors, one of which is the projection of u onto v. So there's really two questions here. One is to find the projection, and then the second is to express u as the sum of these two vectors. Yes, of course. So I'm going to start with the first part, the yellow piece, where we're just going to calculate the projection of u onto v. So we'll just write down the formula. Okay. So let's start by doing the dot product. So that's u dot v is going to be u1 times v1 plus u2 times v2. The magnitude of v is going to be 6 squared plus negative 4 squared, all square rooted. So let's see. 3 times 6 is 18. 1 times negative 4 is negative 4, so that's really 14. 6 squared is 36. Negative 4 squared is 16. 36 plus 16 is 52. Note the squared and the square root just kind of cancel each other out. I could reduce that fraction. Really, I'm going to think about that as like 7 over 26. But when I scalar multiply that in and reduce everything out, what does that get? 7 times 3, so 21 over 13. And then 7 times negative 14 over 3, or 13. So I just reduced the fractions when I did that scalar multiplication there, is how I got those kooky fractions. Just reducing. So that's my answer for the question in yellow. Questions so far? Okay. So then to do the part in green, I'm going to go back and remember that as part of my construction of this projection vector, that I can say the following, or really that W is equal to U minus the projection of V onto U. So my U was 3, 1, and my projection is 21 over 13 and negative 14 over 13. So 3 is 39 over 13, and 39 minus 21 is 18. 1 is 13 over 13, so 13 minus a negative 14 is 27 over 13. So I can say then U is equal to my projection plus this vector W and that's my answer to the green question. As just a quick little aside, if I added these two vectors, 21 plus 18 is 39, divided by 13 is 3, which is the x component for U. Negative 14 plus 27 is 13, so 13 over 13 is 1, which is the y component for U. And if I wanted to take the dot product of these two vectors, you should see that it gives 0, which would confirm that those two vectors are orthogonal, that they meet at a 90-degree angle. Questions here before we move on to the next example? If I get going too fast or there's not something you're not quite sure about or you don't think you understand, please feel free to stop me. It is okay. I know that this is probably all brand new for all of us and is not trivial. So if you have questions about something we're doing, please go ahead and stop me. We can always slow down and I can re-explain or elaborate a little bit.
He's not in my class, by the way. I don't know.
Okay. So here is a more typical story problem example. So it says Kyle is going sledding on a hill with a 25-degree angle of incline. If Kyle and the sled weigh a total of 165 pounds, what amount of force is sliding down the hill? So when I read this, this sounds like a vector projection question because we're asking for like the amount of force going in a specific direction, in this case down a hill. So when I reread this, I'm going to be looking for two vectors. So the first vector I see is this hill vector. I'm going to draw a picture to do this. Not that it's necessary to draw the picture, but I think it'll help give us a little bit of intuition for where you guys are at. I think can be quite helpful. So I have down a hill, so I'm going to draw my vector here going in this direction. It says the angle of incline is 25 degrees. So I know that. And what I really want is the direction for this vector. So that should be 335 then. Does everybody feel okay there? So the only other piece of information is just that Kyle and the sled weigh 165 pounds. That must be somehow my second vector. Physics people in the room. What kind of force generates weight? Gravity. That's correct. And what direction is gravity pulling? Where? Straight down. Yeah. So I'm going to make my other vector here. I'll call that G for gravity. So my gravity vector has magnitude of 165, and the direction for that vector should be 270. Notice that we don't have a magnitude for my hill, right? For the hill vector. And in no place in the problem are we given any indication of how long this hill is. So what do you suppose we're going to choose for the length of or the magnitude for our hill vector? 1. Yeah, we're going to just make it a unit vector. Sergio?
Where did you get the 270 from?
Well, look at the blue angle that I drew. That's where the 270 came from. Is that cool?
Yeah.
Okay. Everybody feel okay with how I've gotten the magnitude and direction for the two vectors and where I pulled the information for the two vectors from in the story problem? This tends to be the most difficult piece. So what we're really going to be asked to do then is we're going to be projecting this vector. There's like my W onto the hill. So that's kind of my picture. Okay. My next step, now that I understand the situation, is going to be to resolve these vectors h and g into component form, because all of my vector calculations that I have are all defined in component form. Everybody okay so far? So when I type this into my calculator, I get these two vectors. Notice this vector g is 0, -165, which you probably could have gotten just from looking at our picture and didn't actually really need to resolve that into component form. Since we knew the magnitude of the vector was 165 and it was pointing straight down, you probably could have come up with 0, -165 on your own, but doing what we did formula-wise is perfectly fine also. Either way of doing it is okay. Okay. So now what I want then, or what I care about, is the force that's going down the hill. So I care about the projection of that gravity vector onto the hill. So we'll do our dot product here. So I'll do my projection calculation and go to my calculator here. So I get 6320 and then -2947. So there's my vector, or part of the gravity vector that's going down the hill. Everybody's okay with that? That's what this projection vector is representing, is the part of the gravity vector that's actually going in the same direction as the hill. So what I want then to figure out how much force is really going down the hill is to just find the magnitude of that vector. So 6973 pounds down the hill. Wait a minute. 6973, that's come up here before, right? I see that number here. What is that number the same as? It's just the dot product. So this leads me to think that the projection of H, well, let's just say, I'm going to do this generically, U onto V is equal to the dot product of U and V. So the magnitude of that projection of U onto V is just the dot product of U and V. Well, not quite. There was something special going on in this situation. What was special about the situation that we just did? Yeah. So if that vector we're projecting onto is a unit vector, then we think that this might be true. And I can already see something here that I'm like, well, nope, probably can't always say that. The dot product is just a number, right? It can be any real number, including what kinds of numbers? Negatives. Can the magnitude of a vector be negative? No, right? Those always have to be non-zero or non-negative answers. So let's just put the absolute value around that dot product. Now that seems like maybe that's true. Let's try to prove that. And if it is true, if we can prove it, we can use this shortcut in any problem where we have a unit vector we're projecting onto. Which would be nice, right? Okay, so we have the magnitude of the projection of U onto V equals the absolute value of the dot product of U and V. Well, let's just say if the magnitude of V is 1. Or not if, let's say let. There. Notice that the vertical bars here are meaning something different on each side, correct? On the left, those are magnitude, and on the right, they're absolute values. I know that's rough. So I'm going to begin my proof by just rewriting the projection as the formula. And right away I notice something. What's the magnitude of V in our situation? 1. So that just is really going to turn into the dot product of U and V times V. Everybody's okay with that? Now remember from before we saw that when we're calculating a magnitude, we can pull a scalar out of that. That's what I'm going to do now. But when I pull that scalar out, I know it's going to create an absolute value around that scalar. Again, because I know that a magnitude can't give me a negative number, so whatever that scalar is has to be positive. What do I notice again? The magnitude of V is 1. So yeah, we can use that shortcut, which is pretty cool, because if we go back to our previous problem, that means right here, all I need to do is the dot product, and I can skip everything else. Nice, Mr. K. I like that one. Yeah, dudes. Everybody cool with that? So again, I showed you how to do it by the definition, like by the book, because you can't always take the shortcut. But we found what we thought looked like a shortcut. We proved that under the right conditions, that shortcut does work. So from now on, if you run into that kind of a situation, you're free to use that shortcut. Let's do another example. Okay, this says a crate is being pulled up a ramp at an angle of elevation of 40 degrees with a force of 100 pounds. The ramp measures 10 feet horizontally and 2 feet vertically. Assuming that the crate is of negligible weight, what is the amount of force directed up the ramp? So again, when we're asking the amount of force directed in a direction or up a ramp or like whatever, this is a projection problem. This is the way this reads to me. Is everybody okay with that? So I'm going to be looking for two vectors. One of them seems pretty clear that it's this crate. So let's draw that in here. So it's pulling up. Let's see. So it seems pretty clear the magnitude of C should be 100 since that's the force and the direction is 40 degrees. And since we're pulling up, I drew my arrow going like up in the first quadrant. So that angle there just is 40 degrees then. Everybody okay with that? Okay. It then says the only other piece of information is that the ramp measures 10 feet horizontally and 2 feet vertically. Well, I guess that must be my second vector somehow. So if I drew that on my picture, like 10, 2 might be, like that. So my projection vector is going to be here. Cool. But this vector R, are we given the magnitude for it? Are we given the direction for it? No. I mean, we could figure those out, I guess. But really what we want for vector R is just its component form. If to draw vector R, I went 10 over and 2 up, that's the component form then, dude. I don't have to muck around with anything. All right. That's rad. I'll take it. You know what I mean? Worth noting, what is the magnitude of r is definitely not 1, right? Remember, the magnitude is just the square root of the x component squared plus the y component squared. Definitely not 1 in this case, right? So we can't use that shortcut that we just developed a moment ago, but that's okay. We can just do this problem the same way we did the previous one. So 7660, and then 64, I missed the other piece, 20 I thought, 28. Okay. Notice that I am not doing the shortcut because my ramp is not a unit vector. So 7660 times 10 plus 6428 times 2, oops, forgot the squared there, over 10 squared plus 2 squared times 10 2. So 8602 for the first component. And 1720 for the second component. So the magnitude then is all I need left. So 8772 pounds up the ramp. So just to summarize again what we're doing here. So we started by taking the story problem and resolving it into two vectors, drawing ourselves a little picture of the situation. The two vectors that we have, we need to resolve into component form. So sometimes in the case of vector r, the component form is basically given to us in the question. And sometimes, like in the case of vector c here, we have to take the magnitude and direction that was given to us and convert it into component form. But once we have our two vectors in component form, we do the appropriate projection. So we fill in the formula to get the projection vector, and then to find the amount of force for that projection vector, we just calculate the magnitude. Is that okay? Again, sometimes taking that big global view and just talking through briefly what it's doing without doing all the details is really helpful. because it's very easy to kind of get bogged down in like, oh, the dot product and then the magnitude and then the scalar multiplication, and just like gets to be a lot. But if you keep in mind, it's easy to get kind of lost in the details if you're not keeping an eye on like, what are we really trying to do overview, which is why that first couple of chapters where we really like converted to different forms of the vectors and did the magnitudes and the directions and did all these calculations. It's important that you feel really good about those first two sections, so that when you get to these more complex problems, doing like a dot product is kind of a trivial task for you. Because if it's all hard, something like this gets overwhelming really quickly. You know what I mean? I'm going to stop here because, quite frankly, this is a kind of a difficult topic, and I don't want to do too much all at once. So at this point, you should be able to do 41 through 50. If you've been looking at the schedule on the, or the agenda on the My Notre Dame, notice we're now behind schedule, which is fine, not a big deal. I forgot everything that went into section 8.3. I just figured I do 2 sections today, and it's like I looked at 8.3, I was like, oh, then it's like I feel probably not wise. I would say, though, now that we've been through 3 sections or so here, homework quiz time, maybe next class or the following would probably be a reasonable time. So it's definitely the first 2 sections, maybe this third one, depending on when that homework quiz falls. So if you are real far behind on the homeworks, you might want to prioritize kind of getting a little bit caught up there and making sure you've done enough that you feel comfortable doing some of these vector calculations. Yeah, Sergio?
What do you want?
What?
When is the test planned for?
Well, I think there's like 8 sections in this chapter, so it's gonna be a bit. So maybe the end of next week or beginning of the week after.
Probably gonna have like 1 or 2 homework chapters.
I mean, it'll be at least 1, right? Could be more than 1, but it's greater than or equal to 1. Not helpful, I know. No, but in all reality, what's the when is the winter break?
I honestly gotta go through.
So that's the 21st through the 25th of February. I would certainly want this chapter wrapped before then. I would think that shouldn't be a problem. And chapter 9 is another quite easy chapter following this one. So that's one that if we start, I don't have a problem starting that before a winter break, because could be something we could literally kind of do in a day if I wanted to, which I probably don't. But we'll certainly want to do chapter 8 test before winter break. Chapter 9, I'm not in a hurry to do that necessarily before break. If that's hanging, that's not a big deal to me.
I don't think anyone really wants to be that math over break.
No, I agree. I mean, I'd prefer not to do that either, but we're just talking, right? Like, it's a flexible schedule, just kind of going at the pace that we're able to go at. We get done what we get done, and we do the best we can. And
I saw that we might get